Hi everyone, thanks for coming. I'm Juan Camilo Rodriguez Duran.
Hi, I'm Bruno Roustan.
And we are search engineers at Salesforce.
So, a journey to write a new Lucene posting format. What is a posting format? It's a Lucene structure a format to store the Lucene inverted index. It's a complex low-level code, a foundation. Why did we need to have a new posting format? We'll talk about challenges, scale, and massive number of fields. Sometimes hard technical challenges are better solved by changing the foundations. And we have such challenges at Salesforce Search. Let's have an overview of our journey to solve them, share our experience with a step backward. First, we would like to thank David Smiley, who is part of the team and was involved in the project. Here is the agenda. On the left, the agenda sections. On the right, the journey map. For each agenda section, we have a line in the map. White bullets represent challenges and solutions, while orange triangle represent issues and obstacles. So first, let's put some context about the scale, number of fields, and the issues. At Salesforce Search, Search as a service is highly multi-tenant at scale. We can have a look at the scale on the right. Massive number of tenants, massive number of Solar shards, and 2,000 online Solar shards per Solar node. That's huge. On top of that, we want to search 150 fields. Why so many fields? Salesforce CRM documents are highly structured and diverse. We have many regular and standard fields, and customers can add many custom fields also. We also support dynamic security rules at field level. That means a user may not be allowed to search on some fields. So that means when we search a query, when we send a query, the list of fields is long and we omit some fields because the user cannot search them. These dynamic security rules are configurable and are pertinent per user. Also, we want to leverage the individual fields to train models to boost per field and increase their relevancy. Finally, we have a search platform and we don't control all the use cases of the customers, so we cannot simplify the number of fields we search. So we have challenging constraints. 2,000 online shards per Solar node, and we want to search 150 fields. Obviously, we started by benchmarking with standard Lucene index approach. And we quickly went out of memory with a very low query throughput. We'll go into the detail, but first, let's have a glimpse of the outcome of our journey and some takeaways. So writing a new posting format, it's doable. Thanks to the Lucene pluggable API, And we didn't have to write everything from scratch. We could reuse many building blocks. We leveraged lots of unit tests from Lucene. This was a success. We created a new posting format, which is extensible, with an extension to support our use case of massive number of fields. And if you plan if you have such a challenge and need to have a new posting format, plan for it. There is a ramp up on the Lucene API, sure, but the test effort is light, and be prepared to significant performance effort. We saw the challenges, the context, the scale, the issues, and at this point of the journey, we were about to investigate for solutions. So we needed an approach first to reduce the memory. Let's have a look at the structure of the Lucene inverted index. On the left, the index layers, they are ordered from top to bottom. And on the right, the index structures corresponding to the layers either on memory or on disk. Let's take an example. We want to search the term big in the field title. Field is the first layer, so we'll first get the index for the field title. Then we'll look up in the index for the term big, first browsing the dictionary prefix tree. And we go to the corresponding block in the term suffixes of the dictionary. There we can get data about the term. Some queries may need additional information. In this case, we have more disk access to access postings, so IDs of documents containing the term, and also positions of the term in all documents. And some queries may need additional data, such as offsets for highlighting, for example, and custom payload. In our use case, we have 150 fields. This means 150 term prefix trees in memory. This is a lot. And this is why we had memory issues. The idea to fix that, yes, is to swap the two first index layers. Make the term the first layer. Let's swap. The field information now is stored in the index. And we have one single prefix tree, sharing all the terms of all the fields. This is very compact compared to having 150 different prefix trees. This is one advantage. There is another advantage. In our use case, we search the same query in all fields. And actually, if we search for the first field, we look up in the index. And then at that point, we are able to gather the data for all fields, actually. We cache that. And then for all subsequent fields, all other fields, we can get the data from the cache and avoid lookups. So basically, we have one single lookup in the dictionary. Going on with the journey, we had the idea, the principle of shared terms. Now we needed to implement or select a way to implement that. Last year, Activate 18, we presented a way. It's to wrap the standard Lucene block tree posting format with a virtual field layer. The idea is to append a field suffix to all terms. So take a term, append a separator, a 0 byte, so every bit 0, and the field ID. This posting format exposes all fields externally, but internally there is one single field containing all the terms composed by the term and field suffix. This does the trick, but with limitations. Because of the 0 byte, we do not support 0 byte in the original term, and also we increase the size of the terms, so actually it increases the size of the prefix tree, the depth. And it has also performance issues. So we wanted another solution. And instead of storing the field information in the term, we could store the field information in the payload. This is a well-supported API, but this has drawbacks. The payload is stored in an additional file. So each time you need to access the information, you need an additional disk access. It costs a lot, and it affects the performance of prefix and wildcard query hugely. Also, we would have to implement or modify most of the Lucene queries to handle the data in the payload. So we chose the other solution to store the field information in the dictionary, in the block, along with the term. The difficulty here is that we needed to modify the dictionary format. So we have a plan. We want to modify the dictionary format. Now, we had three options. Either take the standard Lucene block tree and modify it. It's difficult. Actually, we tried 2 times and failed. It's not designed to be extended or modified. One option we missed, we could have taken another posting format, because there exist posting formats, other than the standard block tree, and try to modify, extend it. One takeaway is that we could have asked earlier the community for feedback and advices. So the solution we chose was to design a new posting format, make it extensible by design, have a base version following the standard layer ordering, and an extension to fulfill our use case for index layer swap. We were ready to design a new posting format. We knew we had to have clear goals. Extensible, have a shared term extension, and also keep in mind that we focus on low memory footprint and the performance for the queries. We focus in our use case term, phrase, and wildcard queries, prefix queries. We leveraged an internship. We brainstormed a lot, yes, for many data structures, many possibilities, and actually, given the performance and memory constraint, we came back to a more classical approach. At that point of the journey, we saw the challenge, we investigated, we were ready to design a new posting format, and now I let Juan explain how we explore the Lucene API and the design of the new posting format.
So first, what is a posting format? A posting format is the way we store the inverted index. So in Lucene, we get the posting format from the codec, and the codec has several parts of the Lucene index, such doc values format, term term vector format, etc. But today, we're just going to focus on the PostingsFormat API. So first thing to know, the PostingsFormat API, it's layered also. So it provides you a fields consumer to write the inverted index and a field producer to read and search on it. So each time you request the terms dictionary for a given field, you will generate inside the fields producer a terms instance. So it will be more clearer if I explain with an example. So again, we're looking for a term big in field title. So inside the field producer, we get a terms instance for the field title, which gives us an Salesforce terms enum, so an iterator, who has two main methods. The first method is the seek, just to position the iterator at the right position, at the right place in the dictionary. And then the second method is next, to get the next term in the dictionary. So in the example, we will instantiate the terms, and inside the terms, an iterator called terms enum, in which we are going to look to the method seek for the term big. So we start to traverse the prefix tree. We get to the right suffix block, and then at this point, we can access the postings. So the postings is the document list, positions, offsets, payloads, etc., represented in Lucene by this class. It's the postings enum class. So this combination between terms enum and postings enum is the way Lucene represents the inverted index. So if we come back to our target posting format, we want to store the fields data after the terms. So hopefully, we can design this new posting format just up to terms enum, because we can reuse the postings enum already given in Lucene, thanks to the Lucene 15 posting reader and writer. So we can reuse a big building block. So OK, now we know which API we have to implement. And now we're going to ask ourselves, hey, but how this new posting format should be? So we thought if make one posting format is challenging, we should make two. But seriously, we wanted a posting format extensible by design. So this base version is called UniformSplit. And later on, I will explain why this name, what's the reason behind this weird name. And then our targeting goal is to have the short terms extension. But why? Why to make a base version? Because we wanted to build reusable foundation blocks, not only for our use case, but for different use cases you may have. So here we see the goals of both posting formats. So the base version UniformSplit, the first goal is to be extensible and very simple, to be used for a general purpose use cases, and to have a low memory footprint. And then we have our short terms UniformSplit extension, whose first goal is to support efficiently a massive number of fields. It should be also simple and extensible, and obviously, it should leverage the parent optimizations. So what is UniformSplit? So UniformSplit is a technique to write the inverted index. So in order to explain that, first, we should remember that for access terms in the dictionary, Lucene stores them in block in order to reduce search space, to be more efficient at lookup time. So the standard block tree posting format uses its own policy to define those blocks based on the term prefixes. With UniformSplit, we use a simple approach. We wanted a uniform number of blocks having a uniform block size. So that's the name. That's the explanation behind the name. We wanted the terms to be distributed in a uniform manner. So then, You may ask, hey, but how can we access those terms in the dictionary? We need a data structure capable to map terms to blocks. So the most simple approach is, hey, you take two aligned arrays, one containing the first term of each block, and the second one just having the file pointer. And each time you make a search, you make traditional binary search. Like, oh, okay, that will work efficiently. But as you may know, this aligned list is not the most efficient way to store this kind of data. As you may see, terms tends to share prefix between them. So as our second goal with UniformSplit was to have low memory footprint and to be competitive with the standard block tree posting format, we reuse the finite state transducers implemented in Lucene as efficiencies to store those special terms that we will define as block keys. So terms that map terms to blocks, so block keys. So we realized that those block keys were quite long. And say, oh, can we reduce its length? And the answer is yes. We realized that if you compare the last term of the previous block with a new block key, you get a minimal distinguishing prefix that allow us to have the same discriminative power, but with a lower cost. So here, as you see, we don't have to use the whole word company. We just have to compare the first three characters, and we have the same discriminative power. Then we check that by having this fixed number of terms, times, we get to a long block key. We say, oh no, this is not possible. Why? But then we realized if we look around a neighborhood to those long block keys, you can find a shorter one. Think, oh, okay. If we look in a neighborhood to the block edges, you can find a local minimum that allow us to reduce further FST footprint in memory. So it was our second optimization. So by having an average uniform block size. So then we start to investigate. Hey, what happened when you get to those blocks? What happened is that you have to decode each term in a sequential order. You say, oh, this is kind of costly. But then we realized we can use a compression technique called incremental encoding. So this technique allows us to reduce block footprint in disk and speed up block loading. How it works? So if we look for example, for the word company, first you get to the block for color, and as you already read color word, and it's in your current buffer, you say, okay, now to get the next term, you have to write at position 2 the empany suffix. In that way, you get the term. I would say, okay, this linear scanning is not very efficient. Can we do something else to improve speed? And the answer is, oh, can we reuse binary search here? The answer is kind of. You can use at least the first step of binary search. So you say, okay, if I first look the middle term of the block, I can know if I have to jump or to early stop in the scan. So just by making one additional comparison, we speed up the block scanning to the half. So it was impressive. So yes, the example here is you're looking for components, you get to the block to color, but you first compare with the word component, and you know you have to jump. So okay, now we have the API clear and the principle of our new posting format clear. So we started to implement it. So coming back to the Lucene PostingsFormat API, let's see how UniformSplit fits in. So as expected, we implemented a class per interface in the Lucene PostingsFormat API. So we have a UniformSplit posting format, UniformSplit terms reader, UniformSplit terms writer. But we implemented the terms enum interface with a block reader, because for us was more clear. But what is important here is that we have a block reader and its counterpart called block writer, both using the same concept of block lines that can be easy extensible to have our chart terms version next. So UniformSplit implementation was quite simple. It took us 17 classes and 1,500 line of code, comparing to the 2,800 line of code of the block tree posting format. And you may ask, hey, does this count include test? Do you make any tests on this? And say, no, we don't make any tests. Say, what? You're crazy, guys. How do you change foundation without writing any test? And say, hopefully, we can reuse the awesome Lucene test framework. So Lucene has a lot of tests, testing a lot of edge cases with recursion, multi-threading, a lot of that stuff. And you can configure the test to run with your code. In this case, the posting format. So it boosts our development in an incredible way. It was, wow, incredible. So the takeaway here, if you're planning to change foundations, leverage the Lucene test, because they are very complete. And each time you run it, they run different things, because they are randomized in addition. So each time you have more coverage. So we have our UniformSplit version, code complete, all tests passed. Now we're going to check how are we going to implement the chart terms extension of UniformSplit. So remember, we will share all terms for all fields in a common terms dictionary. So if we look for the term big for field title, we will traverse the block prefix, the block keys to get the right block. And once we get into the right block, we get to the right block line. At that moment, we will store after the term the field's IDs. So we have just to override this class block line to have our chart terms block line, and override the seek and next methods, just to check if the current term occurs or not for the requested field. So that's it. It was a quite simple extension. And it's reflected on the number of lines of code we use was 600 lines of code and 12 classes. Now you say, OK, we have two posting formats and one containing our target optimization supporting a massive number of fields. All we have to make is just put it in production. But Bruno say, no, you can't do that. You have first to check performance. You say, OK, let's check performance. And as you may see in the plan, it's going to be a little bit challenging. But I let Bruno explain you more what's happened at the last mile effort and what's the difference to be functional complete and production ready.
Performance. This is a journey in itself. So we have a first version that worked, test pass. A second extension worked also. We started benchmarking with IBM robust Java benchmarking. There are other benchmarking tools out there. We compared UniformSplit to block tree, and at that step, we focused on some queries. We focused on term, phrase, and prefix queries. We got encouraging results in both speed and memory, but we didn't have the data volume, the GC, load, analysis, and we didn't count the scoring part of the query. We needed a more thorough benchmark, and there is one available. Lucene Util. It's open source. It's used to compare posting formats in Lucene. And as soon as we started indexing data, creating segments, merging segments, boom. Segments, short-term extension had very bad performance when merging segments. So we investigated. Remember, we swapped the index layers. The default merge is designed for the regular ordering, and it performed very inefficiently when swapping the index layers. Hopefully, we could customize it by overriding the merge method. It adds some complexity, but eventually we fixed the issue and we could merge as fast as normally it's expected. Then we went on with the benchmarking, and we had several GC overhead issues due to object allocation. We realized we had to follow guidelines because at that level, low level in Lucene, we had to take care of object allocations, reuse mutable objects when possible, lazy initialize big objects to not create them and initialize them anytime, avoid lambdas in inner loops, be careful of JavaStream because performance cost is not always obvious. And more important for the index performance, really watch the disk accesses. This is the major part of the speed. So we completed the benchmark. We got results. Interestingly, the speed is good compared to block tree for small to medium index, and same for large index. Why? Actually, it depends on the number of results. When we get more and more results returned by the query, we spend time on accessing the postings and scoring the results. And finally, the dictionary lookup becomes a minor part of the total query time. And we realized that we had an issue with fuzzy query, which was not our focus, but we tried to fix that. Fuzzy query is an automaton-based query, such as other wildcard prefix query. It relies on the terms intersect method, so we tried to customize it. Yeah, actually, we didn't reach the same level of efficiency. The final performance is still poor compared to the block tree which is highly optimized for the fuzzy query. This is a compromise, and we knew we had to be prepared to make compromise. Lucene Util benchmark gave us good measures, but we didn't measure memory nor GC load, and we didn't have disk usage. Then we were ready to test with production benchmark. Not real production, but leveraging the shadow experiment framework we have at Salesforce. We were in the context of shared terms, so many 150 fields, and we used our data volume, data shape. We compared with the standard default implementation with the regular Lucene index. The speed and memory saving is huge, as expected. we also compared with the V1 version we presented last year at Activate 18. And we also gained significantly on both speed and memory. We saw the performance, all the challenges, and now can we get some outcome of the journey and have some takeaways? Yes, it's doable. We have UniformSplit designed to be extensible, and actually we hope it will be extended to other purposes. We have the short term extension to support a massive number of fields, and it is open source since last week. Remember that we have poor spell check fuzzy query performance, but actually we solved that because in our case, we do spell check on only specific fields. So we can use the per field posting format to keep the block tree for those fields. And for all other fields, we can use the uniform split. So if you have some technical challenges and need to change, modify a posting format, it's doable, plan for it. There are other posting formats existing, not only the block tree. You can learn from them, modify, extend them. You don't have to write from scratch. You can reuse building blocks. We saw that we reused the posting reader. You can leverage awesome Lucene tests. Also leverage the benchmark tool, Lucene Util. So the test effort is not heavy. And finally, discuss your ideas with the community earlier than what we did. Thank you.
We have 3 minutes for questions, if you have.
You were talking about the problems with like the prefix trees, and forgive me if I didn't quite understand. Like, how did you arrive that you need to change posting format? How did you arrive that that was a valid way to solve your problems?
So we realized we had an issue because we benchmarked with the standard posting format, the block tree, and for the case of 150 fields, we went out of memory. That was the trigger for investigation. And as we saw, we investigated for solutions. We tried to reuse the existing, modify it, and finally decided to implement a new one.
So you mentioned at the end, like you don't have to rewrite from scratch. Mm-hmm. And at the beginning, you kind of mentioned that you didn't realize that early enough. So right now, did you consolidate with existing code, or is it still kind of separate, the uniform split thing? Is it, I'm curious.
Separate, what do you mean by?
Like you're saying rewriting from scratch versus reusing existing postings format code. But did you manage to do that, or is it still kind of separate? Are they
So I can answer. So as you see, the first part of the posting format, so the part of the terms enum iterator, we rewrite it, and we reuse was the postings, what is called posting this document list, position, offset, payload, was reused. So the main idea and the main mantra behind uniform split is that now you can extend uniform split to other use cases. You can use uniform split, for example, for doc values. You say, okay, those values, I don't need the postings enum API. So you can code it at that moment, and you will have incremental encoding and fast scanning. So the main idea is to try to reuse, because the class is built to be reused for any other use case you may have. Mm-hmm.
Yes.
So this modification is it's good for 150 fields.
Do you have tests that for a normal, like if I only have few fields, will there be any impact or negative impact, or it's also better performance?
For a few fields,
Yeah, for
you
10 fields.
10 fields, you can use the default posting format. That's okay. You may want to use UniformSplit because you need to extend it to add some custom behavior based on.
Does that mean you have to change the configuration during the flight for each search?
No, you have to change the config of Solar, for example, to specify that you want such posting format for such type of field.
But just for answer your question, UniformSplit is faster for the target queries we saw. So term, prefix, and wildcards. And as you saw with fuzzy queries, we have some issues. So if you want to use UniformSplit and you're targeting fuzzy queries, don't use it. Otherwise, you can use it because it's faster. And why we have this chart terms extension? Because our scale, in a normal scale, your servers can handle 150 fields without any problem. But in our scale, having 2,000 online charts in a single Solar server, having more than 20 segments, you cannot use much as 8 megabytes of memory. So at that moment, we saw this bomb out of memory exception.
Yes?
When you say prefix and wildcard, did you include also simultaneous left and right wildcards?
Just as you may think, wildcards, except for the first character, are prefix. And say, okay, this prefix is the same kind of approach, because once you have the first character, it's just a prefix and you check suffix. So, but the problem with fuzzy queries is that you can use the edit distance. So at the moment you have to swap the characters, and at the moment you have to really iterate to the prefix tree. So in that case, in the block keys, to intersect. Oh, this regular expression can be in this block or in this block. And as we reduce the footprint, you say, oh, we have a few characters at the beginning. At that moment, it starts to be costly.
Is this like a phrase or phrase, like phrase queries or wildcards at the end?
For phrase queries, it's very, very good our performance.
It's better.
But phrase queries and phrase wildcard queries.
You mentioned about, I'm sorry, if someone else want to go?
Maybe.
Hopefully, quick question. So you mentioned about memory improvements. Did you, and what about the performance part? Maybe I missed that. Was performance also a concern where the old system, if memory was not a problem, if you had enough memory, would you still go that route and for the performance?
Depends on your query. If there is a gain for term, phrase, and prefix query. And actually, the gain is more visible if you have less results per query. If you have a huge number of results, actually the time is spent in getting the postings or scoring the results, but not really accessing the dictionary, looking up. So depends on the number of results.
If you have more questions, we can discuss outside. Okay, we are run out of time. Thank you very much.
Thank you.